So,
Yes, sir.
Okay, fine. So this is from your syllabus. So we'll for the second law we'll talk about qualitative analysis of heat and work transfer. We'll look into what is an heat engine and a refrigerator. And second law we'll study two different statements. So Kelvin Planck and Clausius statement. So both these statements are about the second law. They describe the second law and what are the difference, what is the similarity, that we'll discuss. We'll also talk about efficiency of an engine, and COP is basically coefficient of performance. So we'll see what it means, how we define that. We'll talk about reversible and irreversible processes. What are the causes of irreversibility? We'll look into Carnot cycle and Carnot theorem. We'll talk about absolute thermodynamic temperature scale and Carnot efficiency and Carnot COP, coefficient of performance. So this is your syllabus. Now let us begin with second law. So these are the basic questions we'll try to answer. We'll see. We'll look at what is the second law of thermodynamics, why this is so important. So this is one of the most important laws in let us say classical physics. Okay, sorry for that. So this law is important. This law is universal, and first of all, why it is required. Okay, so we have already studied the first law. All the processes in nature, they follow the first law. So why do we need the second law at all? Why can't I just use the first law and do all my calculations, right? And what are the implications of the second law? Okay, how we can use second law for practical applications. So let us look at some practical applications. So let us say, for example, I have a cup of tea. Okay, hot cup of tea. So if you leave it in a room, what will happen after some time? The tea will become
Cool, sir.
cold. The tea becomes
cold.
cold. How? Why?
Their heat escapes.
The heat
Heat
Temperature.
transfers.
escapes. So it leaves or it transfers heat. Heat is getting transferred from the tea to the ambient air.
Surrounding.
Surrounding air receives this heat. So because of that, tea goes cold. So what we see here is that air is taking away heat. Okay. Now let us take another example. Let's say instead of tea, I have an ice cream. So what will happen to ice cream if I leave it for some time in ambient temperature?
Melt.
Melt.
It will melt. Why it will melt?
Melt.
Heat is coming.
It is
Because it is receiving heat from the atmosphere. Okay, so what is happening here is it looks confusing. Air is sometimes taking away heat. Air is also supplying heat. So what the air is doing actually, or why? How do I determine what is the difference between these two?
Temperature difference at the
Yes.
lower temperature.
So basically, for both the examples, what we see happening is that heat is getting transferred from a hot body to a cold body. Okay. Now let us talk about the reverse process. Let's say that instead of air taking heat, let us say air gives back heat to the tea. Okay, what will happen? The tea will get hot again, right? But is this possible? Can you get tea heated by air?
no, sir.
No, it is not possible. Okay, but the reverse process, tea, air heating up tea or air cooling the ice cream, both these processes are perfectly fine with the first law. Okay, first law is basically, first law talks about energy conservation, right? So yes, any question is there? Okay, so first law talks about conserving the energy. First law doesn't care about what happens. First law says that whatever process you do, you conserve the energy. So let's say that whatever heat Q was lost, the same U is coming back. If the same Q is coming back, then there is no loss or no violation of the first law. Do you agree to that? If the same Q is coming back, I can heat the tea to the same temperature and first law is not violated.
Yes, sir.
Or let us say the ice cream received Q amount of heat, let it be some kilojoule or joule. The same amount is again lost and it becomes cold. The first law is perfectly fine. First law is not violated here. Energy is balanced. But these processes do not happen. Okay. Now, natural processes take place in what we see is natural processes take place in certain fixed direction. Okay. Not in any random way. So, for example, we see that heat is getting transferred from hot to cold and not on the reverse way. Okay. But the first law does not provide any directional constant. Okay. First law does not says that heat will get transferred from here to here and not from here to here. First law is perfectly fine even if you transfer heat from cold to hot. The only condition for the first law is that energy should be conserved. You should not violate that law. So, but natural processes take place in certain fixed direction that we have seen in the last slide. So, to tell us that, tell us how the natural processes will proceed, we need a law or rule. Okay. Now, this directional constant will be provided by second law. Second law will tell you whether heat will transfer from hot to cold or cold to hot. So by the end of this chapter, you will have mathematical relations which will tell you that ice cream will melt or ice cream will get frozen by the atmosphere. You will have a numerical relation which will tell you that it is natural for this to lose heat, but it is not natural for a tea to gain heat. That is what we'll try to understand in this chapter. Okay, moving on. Now, before we go to formal definitions of the second law, we need to define some devices. So let us start with thermal energy reservoir. Okay, or simply we'll call energy reservoir. So it is basically a large body with infinite heat capacity. Okay, now what do you mean by infinite heat capacity? So we know that Q is equal to mc delta T. So this could be Cp, Cv, anything. But this is what this you all are clear with this equation, right? Now heat capacity is what is highlighted in red, mc. Okay, so we see that delta T is equal to Q by mc. Everyone is okay with this equation?
Yes, sir.
Okay. Now what I am saying here is that I am assuming a device which has infinite heat capacity. Okay, which means the denominator is infinite. So what it means for delta T? If I supply some Q, will the temperature change or will not change?
Not
Not
change.
Because the
Not change,
denominator,
sir.
yes, because the denominator is infinite, delta T will not change. So as a result, this device can absorb or reject unlimited amount of heat. Okay, but the temperature will always remain constant. So this is a special property of thermal energy reservoir. Okay. Now there are two types of reservoirs. One is where which transfer heat to the system. Okay. So we will talk about heat engine. We will see the thermal reservoirs which is transferring heat to the system is called source. Okay. Finally, while we are running the cycle, we need to reject some amount of heat. So that is done to another reservoir which is at a lower temperature, and this is called a sink. Okay, we'll see that in next slide what a source and sink look like. Okay, both are basically thermal reservoirs, but both are at different temperature. So which one will be higher, source or sink?
Source.
Source.
Source will be at a higher temperature, sink will be at a lower temperature. And what are some examples? So for example, atmosphere, large water bodies like lake, river or ocean. So if you consider the last slide, we said that atmosphere is taking heat from the T. So does the temperature of the surrounding air change because of the heat lost by T?
No,
No,
sir.
sir.
No. Similarly, air is supplying heat to the ice cream. Okay, it is acting like a source now, but the temperature remains constant. It is practically constant, right? So these are some examples of thermal energy reservoir. Okay, moving on. So let us now define another device which is called heat engine. Okay, so what is a heat engine? It is a device which converts heat to work. Okay, now it receives heat from high temperature reservoir source that I have mentioned in the last slide. Then it operates on a thermodynamic cycle and produces net work. Okay, and it rejects some heat to the low temperature reservoir which is called sink. So let us see how this looks like schematically. So what you see here is the red box on the top. This is your source and this is your sink. Okay, and this is your heat engine. So what happens is heat engine is receiving some amount of heat, let us say QH. So these are the different temperatures TH and TL, where TH is more than TL. Now TH is supplying some heat QH. So this is your heat engine. Okay, heat engine receives this heat, then using this heat it runs on some cycle and it performs some work W net, and then it rejects some amount of heat. Okay, and it comes back to its initial conditions, and then the cycle continues again. Is this clear to everyone what is going on here?
Yes, sir.
Okay, now what will be the W net? Can I write
Yes,
like this?
sir.
So to give you a very crude example, you can imagine Kirchhoff's law. So I believe you all have studied Kirchhoff's law in your 12th standard physics.
Yes, sir.
So similarly, you can say that this is a node, and whatever heat is coming and leaving is, you need to balance whatever energy is coming and leaving. So what is coming inside? QH is coming and QL and W net are leaving. So what is the net effect? Net effect it should be having zero using Kirchhoff's law. So whatever is coming, whatever energy is coming and whatever is leaving should be balanced. So W net will be equal to QH minus QL. Is this clear? This is a very important way. This is how we'll define work or any net change or net heat gain, heat lost, things like that. Okay, for example, if I don't know QL, if I know W net, I can write QL is equal to QH. Okay, QH is coming. Now W net goes out. So I will say minus W net. So QL is equal to QH minus W. Now here I say that QH and QL are known. So W is defined in that terms. Is this clear to everyone or should I repeat? Clear? Okay. Now let us talk about efficiency of
Yes,
this
sir.
heat engine. Okay. So how do we define thermal efficiency? We say what is the network output, what output we are getting from that engine or that device divided by total heat input, whatever input is being supplied. Okay. So what is the work output here? This, what is the heat or energy that is supplied? Then what is the input? This is the input. Okay. So we say that thermal efficiency, this is the symbol. Beta is efficiency, TH is for thermal. We are talking about thermal efficiency here. That is equal to net work done divided by QH. Okay. Now what is W net? QH minus QL. So that we are substituting here. QH minus QL divided by QH, which is equal to 1 minus QH by QL. This is your thermal efficiency for a heat engine. Okay. Any doubts on this? Fine. So we see that this is how we define thermal efficiency for a heat engine. Now, what you see here, QL. QL is just a wastage of energy, right? We are losing so much of heat. We're just throwing it out. You all agree to that?
Sir.
Yes, sir.
It is just a wastage. I am throwing it out. So, can the question is that as an engineer, we always want to improve efficiency. We want to reduce wastage. So, can we reduce this wastage of energy, or I will go one step further. I will say that can we just eliminate this? Let us say this is not there at all. Okay. So this is the cycle we'll have. We'll have a source, high temperature reservoir, it will supply heat, and I'll say that no QL. Okay. No heat loss. So what will happen is whatever heat is coming, the total heat will get converted to work. Right? Similar to Kirchhoff's law. Now, because of that, if I remove this, my thermal efficiency will become 1 minus 0, which is equal to 100%. Right? So, the question is whether it is possible. No. I cannot have an 100% efficient heat engine. Now we come to second law. So, we'll look at. So, basically, what happens is that you will always have to reject some heat. Okay, because the system has to go back to its initial state. Remember when we defined the cycle, what we said was that the system needs to get restored to the original coordinates. Okay, it will do some work, it will undergo some cycle, but at the end of the cycle, it will come back from where it started. Okay, so for that, you need to reject some heat. Is this clear?
Yes, sir.
Okay, so with that, we come to the first definition or first statement of the second law, which is called Kelvin-Planck statement. So what it says is that it is impossible for any device that operates in a cycle. So this is important. That operates in a cycle to receive heat from a single reservoir and produce net amount of work. Okay. So when you want to produce a net work, then you cannot use a single reservoir. You need to have at least two. You can have more than two. You can have 5, you can have 10, but you cannot have one reservoir. So at least two you should have. Okay. So let me explain or comment on this statement. So what it says is that heat engine producing network and so this is important network and exchanging heat with a single reservoir. Okay, in a cycle it should write. Heat engine basically operates in a cycle. So this is also very key term. I will make this correction. So this is not allowed. Okay. So some amount of heat must be rejected to sink. This is what we discussed in the last slide. And 100% efficient engine is not possible. Okay. So what do you mean? Yes, any question is there? Okay. So what do you mean by 100% efficient engine? Basically, it says that complete conversion of heat to work in a cycle. Okay, that is what we discussed in the last slide. Right? Whatever the heat is coming, that is completely getting converted to work in a cycle. That is not possible.
Sir,
Yes.
the single reservoir means both the sink and the source should be present, no?
Yes. I cannot remove the source. I cannot remove the sink.
Yes.
Okay. Both should be there. Okay. One important observation for the second law is that whatever I have mentioned just now, this limitation for not having 100% efficiency. This is not because of friction or any other such effects. Okay. Even for ideal conditions, this applies both to ideal and practical engines. Even if you assume that it is a massless, frictionless no other losses, still it cannot be 100% efficient. So don't think that this is because of some heat leakage or some internal irreversibility. That is not there. Theoretically, you cannot make 100% efficient engine. Okay, we'll talk in more detail about why in later slides. Okay, moving on. So let us now look at heat and work. Okay.
सर
Yes.
सर सिंगल रिजर्वायर मीन्स बता दीजिए क्या होता है सर.
Single reservoir means, see, you have for heat engine, you have two reservoirs, right? One and two. One is source and one is sink. Okay, let me delete other. So this is a heat engine, what you are seeing here. Okay. Let me write it again. So this is a heat engine. This round device, what you see here, round symbol, this is a heat engine which operates on a cycle. So how many reservoirs you see here? One, two. Two thermal reservoirs are there. One is source, one is sink. Fine.
Yes sir.
So single reservoir means I cannot have only one. I need to have at least these two. Okay, single reservoir means I cannot remove this. I cannot remove this also.
Okay sir. Yes sir.
Okay.
Yes sir. Yes sir.
Single means only one. Okay. Moving on. So let us now talk about heat and work. So the question is, can we completely convert work to heat? Is this possible?
No, sir.
No, sir. Yes, sir.
Sir, read carefully. Work to heat. I'm not talking
Yes,
about
sir.
heat.
Yes, sir.
Work to heat is possible. Okay.
Sir.
For example, we talked about Joule's experiment for the first law, pedal wheel experiment, right? Just go back to those slides and see. In that slide, we have mentioned that whatever pedal wheel work is there, that is completely converted to heat. Okay. Or let us say, for example, friction. So if suppose you rub your hand, or if you rub two objects, so you're doing work on that object, and what happens is it is converted to heat completely. Okay, for a process or in a cycle. Either way, work can always be completely converted to heat. But the reverse is not true. Okay, heat cannot be completely converted to work, especially in a cycle. So next, the question arises is that, is there any qualitative difference, okay, between heat and work? So if something is better than other, basically we define heat as a low grade energy and work as a high grade energy. Okay, so whenever you have a choice, it is always better to have work rather than heat, because you can anyway convert. If you require heat, you can convert work to heat, but the reverse is not true. Okay, so complete conversion of low grade energy to high grade energy in a cycle is impossible. So what we have mentioned, so low grade to high grade you cannot do, but the reverse is true. You can convert this completely, but not this. Okay, is this clear to everyone? This is a very important difference in heat and work. What is a low grade energy and what is a high grade energy?
Sir,
Yes.
sir, why is heat considered as low grade energy?
Because we cannot, so it is basically classified. Okay, why it is classified? Because it cannot be completely converted to high grade. That is the reason.
And sir, why we cannot convert heat into work?
That is what all second law is all about. So we saw in the last slide, right? We cannot convert heat completely to work. Read this. Okay.
Yes, sir.
Because second law stops us. Second law is, this is the basic outcome of the second law. This is one of the consequences of the second law that complete conversion of heat to work is not possible. Okay, so because of that, heat is a low grade energy, work is a high grade energy. Fine. Now let us look some more into the second law. Let us define another device which is called heat pump. Okay. So someone is not muted. Can you please mute? Okay. So heat pump. So it looks like the heat engine, right? Only difference is that the heat supplied is in reverse direction. Heat transfer for heat pump was happening in this direction, but for heat engine, we are having heat transfer in this direction, and heat pump, we are having heat transfer in opposite direction. Okay, so what this device does is that it takes heat from low temperature reservoir. It works on a cycle. So this is your heat pump. Okay, it also operates on a cycle, which is different from heat engine. Basically, it is the reverse form of a heat engine. Okay, so heat engine takes heat from source and transfers to sink. This does the reverse. It takes heat from low temperature reservoir and transfers heat to high temperature reservoir. Okay, is this clear, or is this it looks okay, or any problem is there? Is this possible? Basically, it
Sir,
is.
work done.
Yes, we are coming to that. So basically, heat pump is saying that it is transferring. What is the net effect? It is transferring heat from low temperature to high temperature. Okay, is this possible? Can we design a device or any application which can transfer heat from low temperature to high temperature?
Yes, sir.
Refrigerator.
Yes, correct. So we have refrigerator, we have AC. So both this transferring heat from colder to hotter body. But one important point here is that it requires electricity. Okay, it requires some sort of work input. Without that, it will not work. Right? So if you understand this, then you understand the second statement of second law, which is Clausius statement. So let us go to that. Before that, this is your heat pump. Let us define the heat pump. So it requires some amount of work input. Without this work, it will not work. So let us now define the heat engine, a heat pump. So heat pump is a device which transfers heat from low temperature to high temperature. It works on a thermodynamic cycle similar to a heat engine. Only the difference is that the cycle will be reversed. It requires work input to function, and efficiency is measured in coefficient of performance, COP. Okay. So how do we define COP for a heat pump? We say that COP is ratio of desired output and required input. Whatever the input is applied and whatever the output we obtain. So what is the output here? Can anyone guess?
QH.
QH. Okay, so this is the objective is to heat up this. So QH is the output, and what is the input?
Work done.
The
H
work
minus
done on the
QL.
system. It will be QH by W, and W is QH minus QL. This is the COP for a heat pump. Okay. So with that, now let us go back to the second law. So there is another statement of second law which is called Clausius statement. Okay, so what it says is that it is impossible to construct a device that operates in a cycle. So this is important, and produces no effect other than the transfer of heat from a cooler body to a hotter body. Okay, so this is like a historical statement given by Clausius, but we'll interpret it. We'll try to understand what he was trying to say. So what he meant was that all natural and spontaneous processes, okay, heat transfer is from hot body to cold body. This we have seen in the case of ice cream and tea. This is what happens. Now, the processes which are not natural or which are not spontaneous. So spontaneous is another term for a natural process. Okay. All these processes need external help in the form of work. Okay. Now, AC or refrigeration, this is not natural. This is artificially we are cooling the room. Artificially we are cooling the content inside the refrigerator. Now, for that artificial process to happen, we need electricity. We need work input. It will not work without electricity. Okay. So, the interpretation of this statement is that, okay, you can transfer heat from cold body to hot body, but to make that happen, there need to be some work input. Okay, it is not possible that there is no other effect. Some effect is there, and that is your work input. You need to supply work to the system for this to be possible. Okay, this happens naturally. If I want to do this, I need to supply some work. This is the meaning or interpretation of Gaussian statement.
Sir,
Yes.
sir, is it really possible to transfer the heat from the cold body to hot? Even in the refrigerator, if you look at the core
Yes.
point, it works
Yes.
on the Joule Thomson, I think. And the
No.
molecule.
Okay. We will talk about. Let us go to the refrigerator. We'll talk about the cycle on which it works, but let us look at the overall effect. Okay.
Overall,
Let me finish. Let me finish. So what happens in a refrigerator? What is the overall functioning? Or let us talk about this AC. Okay, this is a simple example.
okay.
Let us say you are sitting in a room. Okay, what is the temperature of the room? Or let us say you have AC installed. What is the temperature of the room? Let's say you set 20 degrees Celsius. Right? What will be the outside temperature? Let us say 40. Fine. You are okay with this?
Yes, sir.
Now, have you seen AC from backside? Have you seen
Yes,
that?
sir. Window
It is
outdoor.
outdoor, so it is throwing out heat.
Yes, sir. Hot air.
Yes. So it pushes out hot air. What the hot air is doing? It is heating the ambient. Hot air is being thrown out from the AC, right? Here it is providing cold air. Here it is providing hot air. Hot air means it is heating the ambient. It is heating the atmosphere. So atmosphere is at high temperature. Atmosphere is at TH. Okay. Your room is at, this is at TL. TH and TL are defined such that TH is greater than TL, right?
Yes, sir. I'm getting that. What I wanted to tell that we use the natural phenomena in that physics also. At the core, uh, according to the Joule Thomson, air molecules are going too far apart.
No, we will not talk about Joule Thomson. Forget about Joule Thomson. Okay. Let us
Okay.
talk what is the net effect of an air conditioner. What is the air conditioner is doing here? Air conditioner is cooling your room.
Yes, sir. Net effect is the same. But
So
cool. Yes, sir.
okay, don't get confused. Joule Thomson will talk about. That is a separate topic. We'll go to that. But let me complete this. So what I'm trying to say is net effect for a AC or a refrigerator will be to transfer heat. Okay, so what happens is that you are sitting in a room because of air heat leakage, it will also get heated up. Okay, outside is 40, this is 20. So some heat will always be leaking inside. Now what we need to do is we need to remove that heat because of the cooling effect. So it provides you cooling air. Basically it is removing the heat, and where that heat is going, that heat is going here. It is throwing the heat outside. Okay, so we will anyway study the working cycle for a refrigerator or AC. That comes, I think, in you need to wait for two more chapters. Okay, but before we go to that, the net effect that we must agree on. Net effect is that it is transferring heat from low temperature to high temperature. Isn't it?
Yes, sir.
So let us focus on this. It is transferring heat from low temperature to high temperature. That is the effect of AC or fridge. So this is what we're talking about here. You can do that. You can transfer heat from cold to hot, but you need some work input. That is all I am saying. That is the essence of Clausius statement of second law. Okay? You are clear now, or again some doubt is there?
Sir, I got net effect the same. I will ask you
Yeah.
in last of the after the class.
Yes. Yes, fine. We anyway, when we go to Joule Thomson, then you can discuss if you have any doubt. But let us now just focus on heat transfer only. Okay. Moving on. So we talked about two different statements. We talked about Kelvin Planck and we talked about Clausius statement. Okay. So they talk about different things. Kelvin Planck talks about heat engine. Clausius statement talks about refrigerator. Now the question is that whether these two statements are for the same law. Okay. So let us not try to see whether these two statements are equivalent or what happens when you violate one. What happens? Okay. So let us start with the Kelvin Planck. Okay. Let us say that I have a heat engine which takes heat from the hot reservoir and it converts it 100% to work. So what statement is being violated here?
Kelvin Planck.
So it violates Kelvin Planck. It is 100% efficient engine and it is transferring heat completely to work. Okay. So let us start with that. And what we'll do is we'll add one heat pump. Okay. So we'll add a heat pump to this such that the heat pump is operating between TH and TL. Okay. So now the heat pump will take QL from this. It also receive this work. So whatever work output it is giving, let us use this for running heat pump. Okay. So here we have got QH. Here we have got QL. So net again Kirchhoff's law. It is actually not Kirchhoff's law, but similar to that. So we see that the total heat that is transferred to TH is QH plus QL. Right? Is this fine to everyone?
Yes, sir.
Okay. Now, if we combine these two, let us say instead of having two different devices, I make one device which has both these two components. So what will happen? It will be an equivalent heat pump. Okay. Now, what is the net effect? It is taking QL from the low temperature reservoir. What is the net heat transferred to TH? So QH is coming, QH is going back. So net heat is QL. So QL is being supplied to the hot reservoir. Now we have an equivalent heat pump which transfers heat from cold body to hot body without any work input. So what law it violates? What statement it violates?
Clausius.
Clausius.
So we see that we started with an engine which violates Kelvin Planck, and with some modification we end up with a device which is violating Clausius. So we can say that violation of Kelvin Planck leads to violation of Clausius. Okay, now let us look at a different device. Let us say we start with a device heat pump which violates Clausius statement. Okay, how it is violating here? Can anyone tell?
No
Work
work
done.
input.
No work done.
No work.
So
No
it
work.
is, yes, so it is simply taking some heat from the low temperature reservoir and it is applying the same heat to TH. It does not require any work input. So that's why it is violating Clausius statement. So let us add a heat engine to it. Okay. So we can have a heat engine which will take the same amount of heat QH. It will perform some work and reject some heat QL. Fine. Now what we can do? Here, this heat pump is giving QH heat, it is rejecting this heat and this is receiving that heat. What I can do is I can again make a one bigger device which will combine these two. With that, I can remove this reservoir. Okay, I can say that heat supplied, I can turn it back. So I will end up with an equivalent heat engine, okay, which is transferring heat from TL. What is the net heat transferred? QH is going down, QH is coming up. So the net heat transfer will be QH minus QL, right? This minus this. Okay. On the top, TH, I don't need TH. I can supply heat from here to here. So I have a heat engine which is producing net work and which is interacting with only one single reservoir. So this is called single reservoir. So does it violate any statement?
Kelvin Planck.
Single reservoir
Yes.
statement.
So it violates Kelvin-Planck statement. Okay. So what we see from last two slides is that if you violate Clausius statement, it will ultimately lead to the violation of Kelvin-Planck statement, or if you violate Kelvin-Planck, it will lead to the violation of Clausius statement. Okay, so based on this, we can say that these two statements are equivalent and they are concerned with the same law. What law is that? Second law. Second law of thermodynamics is what is getting defined in these two statements. Okay, is everyone clear with that?
Yes, sir.
So
Okay, so there are two statements. So the next question which arises is there any property involved? What are these two statements talking about? There should be something common, right? What is that something is? This is called entropy. Okay, but we'll not talk about entropy today. This is a subject of your next chapter. So we'll come back to the second law. We'll see how it defines, what are its consequences, and what are its applications. So again, we'll talk about perpetual motion machine of the second kind. So first kind we defined which violates the first law. Now we defined second kind which violates the second law. Okay. So any heat engine, what we talked about in the last slides. So any heat engine or heat pump or any device which violates second law of thermodynamics, that is classified as PMM2. Okay. So as we know that it is not possible to violate the second law. So it is not possible to create a PMM which works. So there are many conceptual designs. So people have patented a lot of ideas, but at the end of the day, this will not work. Okay, because it violates second law. Moving on, let us talk a bit about heat pump and refrigerator. Okay, so heat pump and refrigerator, they are. Sorry, I have a bad throat today. So if you are not clearly able to hear, just let me know. I will repeat. Okay. Now coming to heat pump and refrigerator. So these are similar devices. Okay, they operate on the same cycle and cause the same effect. Transfer of heat from cold to hot body. Now, what is the difference? The difference is what is their objective. Okay. Heat pump, the major objective is to supply heat. Okay, so QH is the major objective of heat pump. Transfer heat to the hotter body. And what do you require a refrigerator to do, or refrigerator or air conditioner? It is required to extract heat from cool body, cool the cooler body. So although they operate on a same cycle, they work on the same principle, but their objective is different. So this is for heat pump, and this is the objective for heat refrigerator. Is this clear? The net effect is the same, but their objective is different. Is it clear to everyone? You people are here?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, fine.
Yes, sir.
So any questions on this slide? No. So what will happen? Will it affect the COP of refrigerator?
No,
Okay, so COP heat pump we define in such a way. So COP is basically your desired output. So for heat pump, the desired output is QH. What is the desired output for a refrigerator?
QL.
QL. So the COP
Maximum fuel.
refrigerator will change. So instead of QH, it has QL here. Okay. Now I will give you a statement and you have to prove this at your homework. Basically, you have to show that heat pump COP is refrigerator COP plus 1. So by simple algebraic manipulation, you can show that this quantity is equal to this minus 1. That is what is mentioned here. So this is a very important result for heat engine and heat pump and refrigerator. Okay. So you can try yourself and see. It is a quite easy exercise. You can just subtract this minus this, you will get 1. Okay. Moving on. So another interesting question. What is thermodynamically more efficient? So I have an 1 kilowatt electric heater or a heat pump that uses 1 kilowatt. What do you think is more efficient?
Heat pump.
heat
Heat
pump.
pump.
Heat pump.
Why?
Heat pump.
सर
Because
बिकॉज
it's
हीट
converting
पंप
work
का एफिशिएंसी
into
ज्यादा
low.
होती है.
Sorry, one person at a time.
So efficiency of heat pump is greater.
Greater than what?
मतलब मैं सब पढ़ा था मतलब पहले 12th में.
Okay. Okay. So 12th में how we have studied anyway. So basically in the last line what you see, COP of a heat pump
Heat
is
pump में
1 plus this.
work.
Okay. Let me explain. So refrigerator COP will be some number, but it will be always greater than 0, right? It is actually greater than 1 also, but let us say this is greater than 0. So if this is greater than 0, COP of heat pump can I write is more than 1? Can I write like that? COP of heat is more than 1.
Yes, sir.
Okay. Now if you use a electrical heater, you will get only 1 kilowatt. But if you use a heat pump, you will get more than that because COP is more than 1. Okay, just think about it. We'll discuss this again. Moving on. Now let us. Okay, anyway, you have any class after this, or can I take 5-10 minutes more?
So you can take no class.
Okay, fine. So let us try to finish some of these topics. So we'll talk about
No,
reversible and.
please discuss it once. Electrical heater and heat pump.
I want you to think about it. Okay, I am giving you a hint. Think about it. I will talk about it later. So I'm giving you a hint that COP of heat pump is more than 1. Okay. This is more than 0. So 0, anything, any number plus 1 will be more than 1. Right? You understand what I'm saying?
Yes, sir.
Yes, sir.
So COP of heat pump will always be more than 1. Now if you have a 1 kilowatt electric heater, the total heat it will supply will be 1 kilowatt. But if you give 1 kilowatt of energy to a heat pump, okay, what it means? COP, what it means? COP means, let me delete all that, then it will be more clear. Okay. What do you mean by COP basically is, what is the ratio of work and heat? So I can say W is equal to, sorry, I want to talk about heat, right? So I will say, based on the definition of COP, I can say that heat supplied. This is what I'm interested in, right? Heat supplied will be equal to W into COP. Okay, I'll just take it there. W multiplied by COP. This is okay. Now, if this COP is more than 1, then can I say Q is more than W?
Yes, sir.
Yes. So let us say I supply 1 kilowatt of electrical power, which is W. So the heat supplied will be more than 1 kilowatt. For a heat pump. Do you agree with this? If W is 1 kilowatt, so can I say QH is more than 1 kilowatt?
Yes, sir.
Yes.
Yes, sir.
Now for an electrical heater, the heat supplied will be 1 kilowatt only. It will not be more than 1 kilowatt. But for a heat pump, it will be more than 1 kilowatt. So this is better to have.
Got it, sir.
Fine. Okay, move on. So let us talk about reversible and irreversible processes. Okay. So let us take an example. So let's say you have a pendulum which is moving in vacuum. And there is a pendulum which is in air. So what is the difference? This pendulum can keep on oscillating indefinitely because there's no dissipation, there's no energy loss, so it can go on rotating. While this pendulum, if you have pendulum in air, it will stop after some time, right? This is you all agree to this?
Yes, sir.
Sir.
Yes, sir.
Okay.
Damn God.
So what we can say is that if you are running or operating a pendulum in vacuum, there is no effect in the surrounding because there is no air, no friction. While because air is surrounding this, there is friction with that, this will get tanned. So it affects the surrounding. Right? So which one is reversible and which one is irreversible?
The first one is reversible.
So this one is reversible, this is irreversible. Okay, now let us look at the definition. So a process that can be reversed without leaving any trace, it does not affect the surrounding at all. There is no trace. So you cannot find out whether that process has taken place or not if it is reversed, because it does not leave any trace or any change to the surrounding. Similarly, I can define an irreversible process which it cannot be reversed without leaving any trace. It will always have some impact on the surrounding, either on the system or the surrounding. It will change it. Okay. Now let us look at what are the causes for irreversibility. So we can have either lack of equilibrium during the process. Okay, you can do it very fast. Pressure was not balanced, force was not balanced. Or you could have dissipative effects. For example, friction. Friction will always dissipate some energy. So your process is never reversible. Okay. One more thing is all natural processes are irreversible. For any process, you will mostly have, you are definitely having a, for any practical or natural process, this will definitely be there. Okay. So whatever reversible process we talk about, these are idealized. They do not happen in nature, but ideally we hypothesize that this process, let us say this is reversible. But all natural processes are basically irreversible. Okay. Now let us look at kinds of why irreversibility happened. So one is because lack of equilibrium. Okay. So you could have heat transfer through a finite temperature difference, or there's a lack of pressure. Either you can have a temperature difference or you could have a force difference, pressure difference. So there could be lack of pressure equilibrium within the system or between system and surrounding. So system and surrounding is easy. You have piston cylinder arrangement. Okay. Now let us say it is balanced. I increase the pressure suddenly to a very large value. So this is not balanced. It is much higher than atmosphere. It will just pop out. So then there's a lack of equilibrium between system and surrounding. That is what happens. Now another example is that suppose I increase the pressure so suddenly that there is some pressure here and the pressure here is not the same. So it takes some time. So that is called lack of equilibrium inside the system. This is happening within the system. Okay. Another example is free expansion. So if you have two partitions, one is vacuum, one is having some gas. If I remove this partition, it expands freely. So that is also, that gives rise to irreversibility. You cannot move all the gas back and make this partition again. Okay, so this becomes irreversible. Now let us talk about irreversibility due to dissipative effects. So there could be friction, there could be paddle wheel work transfer. So friction anyway you will lose amount of heat or work. Paddle wheel is also what we do in paddle wheel. Anyone remember what was the objective of this experiment? We studied in the first law.
So increase temperature of water.
So basically, we are converting work to heat, right? This is what we are doing in this experiment. We are using some work of the falling weight, and that is getting transferred to heat. Now I cannot reverse it. I cannot transfer the heat and convert it to work. So that's why it is irreversible. This is dissipative effect. Now another interesting thing is transfer of electricity through a resistor. So what will happen if I pass some electricity? What will happen to the resistor?
Heat up.
It will heat up, sir.
It will heat up. That heat will be lost to the surrounding, so that it becomes irreversible. Okay. Now there are two types of irreversibility: internal and external. Okay. Internal is caused by internal dissipative effects like friction, electrical resistance, which are within the system. Okay. System itself is not able to return back to its original state. Now external irreversibility is irreversibility, that is, there are some typos which I will correct. So this refers to irreversibility which occurring at system boundary. Okay, like heat transfer at finite delta T, like loss of pressure force equilibrium. So these are the two types of irreversibility. So for example, some cycles you could have that are internally reversible. Okay, at the end of the cycle, the system will come back to its original state, but it will leave some trace on the surrounding. So it will not be externally reversible. And while we'll also talk about some examples which are both internally and externally reversible. So are you clear with this?
Yes, sir.
Yes, sir.
Fine. So there's a very important aspect of time. Okay. So a reversible process, it has to be carried infinitely slowly. Okay, with infinitesimal gradient, so that every state passes through equilibrium state. Okay, whatever the system passes through is equilibrium state. Remember we talked about this quasi steady. So if I draw a solid line, it means that all the points here are equilibrium points. And hence reversible process coincides with quasi static. Okay. Now, another interesting point is that if we allow a lot of time, if we say that I have infinite time to for the process to occur, okay, even though finite gradient, this is important. So you can have finite gradient, but you need to have infinite time. So let us say that the piston moves out in 1000 years. The process can still be reversible. Okay. However, if you want to move the piston very fast, if the time available is small, the process will become irreversible because it will not achieve equilibrium. It will be a non-equilibrium process. Okay. Are you clear with this?
Yes, sir.
Fine. So the most important point for a process to be reversible is time. How much time you are allowing? Theoretically, we say that we have infinite time. That is a theoretical approximation, such that your process is very slow and hence it becomes reversible. But naturally, all natural processes are taking place in finite time and all the natural processes are irreversible. This is a theoretical concept. This is a theoretical approximation. Fine. Now, should we get to Carnot cycle? I will need 5 more minutes. Let us quickly look at it, and then in the next class, I will talk about more detail. Okay. So let us see what a Carnot cycle looks like. So PV diagrams we have already seen how to make. So this is a cycle, right? Now let us see what are the processes involved. Okay, so from 1 to 2, what it says is temperature is constant, right? So what process is that? If the temperature is constant,
Isothermal.
Isothermal.
isothermal heat addition. Some heat is getting added. So let us say I have a piston cylinder arrangement where we have this Carnot cycle. Let us say this is a heat engine. Heat engine is operating on a Carnot cycle. Okay. So we have TH and we have TL. This is the basic schematic of a engine which is operating on Carnot cycle. So let us say there you can write Q in or Q out or QH or QL. So this is the first process. Heat is getting from hot source to your system at constant temperature. Okay. Process 1 to 2. Now let us look at process 2 to 3. This is called isentropic process. Okay. So isentropic means that entropy is constant or it is reversible adiabatic. Adiabatic means that there is no heat transfer. Okay. So what we can imagine is that we have a piston which has this wall is only conducting. Okay. So I can transfer heat through this wall or I can insulate that wall so no heat will be transferred. This is basically isentropic. This is expansion or compression. Can anyone tell me? Process 2 to 3.
Expansion, sir.
Function.
Expansion. So we heat from 1 to 2 and then we allow it to expand further isentropically or adiabatically by putting this insulation. So it expands and then we'll go to the next process which is 3 to 4. So what is happening here? We are taking out heat. This process. We are taking out heat from the engine. Okay. And it is expansion or contraction?
Contraction.
Contraction.
Contraction. And it is taking place at constant temperature. So I can call it what I can call
Isothermal contraction.
isothermal. So again I will now this sink comes into picture. Sink is here. This is source and this is sink. So I transfer heat or I reject heat to the sink isothermally. Okay, so this is the third process. 0.3 to 0.4. So let us talk about the last process, which is again isentropic, and this is compression. So what we'll do is we'll let it go inside, it will get compressed, and there's no heat transfer. So it happens isentropically. So if I want to list out all these 4 processes in the cycle, 1 to 2 is isothermal heat addition, 2 to 3 is isentropic expansion, 3 to 4 is isothermal heat rejection, and 4 to 1 is, this is 4 to 1 is isentropic compression. You all are clear with these processes? How these processes are taking place in what order?
Yes, sir.
Okay, fine. Now we talked about PV diagram only. This is PV diagram. Now we can also draw this cycle in a TS diagram. So this is temperature and this is entropy. Okay. Now let me draw that schematic again. So this is your heat engine which is working on a Carnot cycle. So it operates between TL and TH. Okay. It is taking some heat from TH. It is rejecting some heat to here. This is your heat engine working on Carnot cycle. Okay. Now, if I want to draw this on a TS plot, what I can show is, so 1 to 2 is isothermal heat addition. Heat is constant at TH. Okay. TH from the source. So we'll TS plot will mark T. We'll say that the heat is constant. Entropy is changing, but the temperature is constant from 1 to 2. Again, then we'll talk about isentropic, means the entropy is constant. So when you draw it, entropy is the x-axis, then I can draw straight line here. Right? So basically we have 2 processes which are isothermal, 2 processes which are isentropic. So if I have xy axis for T and S, I can say that 2 lines will be isothermal. Okay, so T is constant to TH and TL, and 2 lines which are isentropic. So S is constant. Right? Any questions on this? You all are clear what we discussed just now? What are the various steps of Carnot cycle?
Yes, sir.
Yes. I was having some question. Okay. So a very crucial point here is that we are talking about isothermal heat transfer. Okay. So it is externally reversible. So a very advantageous point, a very difficult point is that isothermal heat transfer is externally reversible, but it is difficult to achieve in practical devices. Okay, so what will happen is that you need to allow infinite time for this to happen. Okay. So with that, let us stop for today. We'll talk about Carnot efficiency next class tomorrow. Fine. Any questions on what we've discussed till now?
Sir?